We looked at functions briefly earlier in the term. Now we'll look at them more thoroughly. A function is a relationship between two sets or variables in which each member of the first set, or the first variable, corresponds to exactly one member of the second set or second variable. And it's this exactly one member relationship that is important for understanding the definition of a function. Let's look at two examples involving things we all should be fairly familiar with. For instance, one situation where we have a student who took a Math 65 class in summer 2019 corresponding to their grade in the class. So the idea is we've got a set of students and they're going to correspond to their grades in the class. So you could imagine different students. Say you could have a student Latifa who got an A in the class. Maybe you have a student named Armand who got a B, and maybe you had a student named Malika who got a C. What we have here is that each student by the end of the term has to get a grade in the class. So each student is getting exactly one assignment to a grade. Each value in the first set corresponds to exactly one value in the second set. Now this is true even if, say, Malika, instead of getting a C, had gotten an A. Malika is still corresponding to a single grade. Even though Latifa and Malika are both corresponding to the same grade, they don't disobey the rule of what a function is because individually each of them is assigned to a single grade. One particular student, like maybe Hector got a B in the class, but he can't at the same time get a B and a C. That would be against the rules for being a function. And if you think about it, you aren't going to get two grades for the same class in a particular term. You're going to have to get a single grade. So the example of a student corresponding to their grade for a particular class has to be a function because each student has to get a single grade, one grade and only one grade. So that's what we mean by each member of the first set corresponds to exactly one member of the second set. That's a function. In our second example, a student corresponding to their telephone number, this is actually going to disobey the rule, and this can help us, especially when you see something disobey the rule, help you understand the rule. Maybe Latifa has a cell phone, and that's her only phone. But Armand has a cell phone, and maybe he's also got a business phone. So it is possible that a student might have two different phones, and maybe Hector has no phone at all. So he doesn't correspond to anybody. So what we have here is students corresponding to one, two, or no phones. And remember, to be a function, each student needs to correspond to exactly one of the second set. And what we have is people corresponding to more than one or even nothing in the second set. So that's why a student corresponding to their telephone number would not be a function. So sometimes seeing a couple of examples can really clarify a definition. But of course, functions are going to be defined as equations, as graphs, as sets of ordered pairs, as well as in real-world scenarios like this. So we're going to be looking at multiple examples of how we tell whether something is a function or not, based on different ways of looking at that function and having it defined. Let's say we have some relationships defined graphically, and we want to know whether those relationships are functions or not. Here we have two graphs. We have kind of a sideways parabola and then this graph that kind of bounces around. Recall, to be a function, each member of the first set, which in a graph would be the x value, must correspond to a single value in the second set, exactly one member of the second set. So it has to correspond to exactly one y. If x corresponds to two different y's, we've got a problem. That is not a function. Okay, so we can only have x corresponding to a single value. Well, an x value in a graph is going to relate to a vertical line. The reason for that is that an x value relates to an x on the x value on the x-axis. So like x equals 3 is here, but x is also 3 here and all the way up and down this vertical line. So one of the things we can look at when we're trying to see if an x value corresponds to more than one point is we can look to see in any vertical line, will the graph that we're examining in terms of the relationship cross in more than one spot. And here, that vertical line crosses in 2 spots. So this is not a function, because what we have for x equals 3 is we have 2 y values at that x equals 3 value. This is called using a vertical line or using a vertical line test to determine if a graph represents a function. A vertical line just represents a single x value. So if that vertical line crosses in more than one spot, that x value is corresponding to more than one y value. Looking at our second graph, if I were to pass a vertical line, sorry, my lines aren't very vertical, but any vertical line going through this graph would only hit the graph in one spot. So here's one spot, one spot, one spot, etc. So because any vertical line would only hit the graph in one spot, this is a function. This graph passes, we would say passes the vertical line test. Sometimes a relationship is defined as a set of ordered pairs. To define a set this way, we would write out ordered pairs with a comma in between them, and then notice there's a brace on either side. Okay, so this is one set, and then this on the right would be a second set. So these are two relationships defined as ordered pairs. We say defined numerically because the ordered pairs are listed as numbers. With ordered pairs, a little reminder, like with 0, 4, the first number relates to x, the second number relates to y. Okay, they're going to be ordered in that way throughout the relationship. So every point is going to be x first, then y. Technically, it doesn't have to be x and y. It could be s and t or any two variables, but it's commonly x and y. To determine if this is a function, a good way to do that is to map out what you see in terms of these ordered pairs. So 0 is an x value, it maps to 4. 1 is another x value, it maps to 3. 2 maps to 5. 3 maps to 3. And 4 maps to 5. Now, notice I already had a 3 and a 5 here, so sometimes people prefer to show going up to the value you already had written. So because 3 goes to 3, I could actually write 3 going to this 3, and I could have 4 going to this 5. Now, what we have here is each x value getting mapped to a y value, and they each get mapped to a single y value. So this is a function. We don't have any x value here that corresponds or maps to more than one y value. And remember, that's the thing. Each x value has to go to a y value. You can't have an x value going to two separate y values. This is the thing you need to avoid. You can't have that. So this first relationship was fine. Let's look at the second one. 1 goes to 2. 2 also goes to 2, so I'll write it that way. 3 goes to 4. 5 goes to 6. And then notice 3 pops up again, and it goes to 7. So because 3 pops up again, I actually use that 3 a second time to go to 7. Here we have an x value, 3, going to two separate y values. That makes this not a function. A relationship can also be expressed as an equation, in other words, algebraically. To be a function, we still have the same rule. Each x value must correspond to exactly one y value and no more than one y value. So we're looking for x to correspond to a single y. We do not want x to correspond to two different y values. That is the no-no right there. You can't have that. So with an equation, the trick to see what you've got is to isolate y using standard algebra rules. So 3x plus 4y equals 12 is our first equation. Let's see what happens when we isolate y. first move the 3x over. It's tradition in mathematics to put, when you're writing sides of equations, to put the variable before the constant there. Now we want to divide out the 4. When you divide out the 4, you want to divide everything by 4. A little reminder there. So we get y equals negative 3/4 x plus 3, because 12 divided by 4 is 3. If we were to put an x value in here and calculate, we would get a single y value. So each x is going to be calculated and give us a single y value, so this is a function. In our next example, where we have x squared plus y squared equals 9, if we solve for y squared by first moving the x squared to the other side, the second step would be to get rid of the square. And a little reminder about numbers that are squared. The square will actually eliminate a sign. So 3 squared is equal to 9, and negative 3 squared is equal to 9. So when you go to do the opposite and square root 9, if you want to get back to all possible values that were there, you have to go plus or minus the square root of 9 to get back to plus or minus 3. So when you undo a square in an equation by square rooting, you must not only square root the stuff on the other side, but you must have a plus or a minus there. So you're going to get 2 results for y for a single x. So this is a scenario, because of the plus and minus, where you have something that is not a function. That plus and minus means that you've got 2 y values for a lot of x values.